Dear students, in this lecture, we are going to discuss about delta connection. What is the relationship between phase and line voltages in a as well as phase and line currents in a delta connected system. So what is delta connected system? What is delta connected system means the starting end of one phase is being joined to finishing end of another phase. This connection is nothing but delta connection. The starting end of one phase is being joined to the finishing end of the another phase. So here we will observe the starting point of one phase is being joined to another finishing point of another phase. Similarly, second phase, the starting point of one phase is being joined to finishing point of another phase. So starting point of one phase is being joined to finishing end of another phase. So in this way, delta connection will be formed. In this way, delta connection will be formed. So here R phase VRN is nothing but R phase voltage, VYN is nothing but Y phase voltage, VBN is nothing but B phase voltages. These three are the phase voltages. Similarly, I1, I2, I3 are the phase currents. I1, I2, I3 are the phase currents. VR, VY, VB are the phase voltages. For three-phase balanced system, as we know that three-phase voltages are equal. VR equals to VY equals to VB equals to V phase. For three-phase balanced system, similarly phase currents also same. I1 equals to I2 equals to I3 equals to I phase. Here we will observe this is the R phase, this is the Y phase, this is the B phase. So IR is the current flowing through the R line. R line. These are the lines: R line, Y line, and B line. Three lines, three phases. So IR is the current flowing through the R line. Similarly, IR is the line current in Y line. Similarly, IY, this is the IY, this is the IB. Here we will see the phase currents are I1, I2, I3, respected phase currents I1, I2, I3. Similarly, line currents are IR, IY, IB. Similarly, VRY is nothing but line voltage between the two lines. Between these two lines, VRY, between the R phase and Y phase, VRY line voltage. Similarly, between the Y phase and B phase, line voltage VYB. Between these two phases, VBR, between B phase and R phase, VBR. Now we will see the what is the relationship between phase and line quantities. First, we will see the phase and line voltages in delta connected system. Relationship between phase and line voltages in a delta connection system. So, as we have defined, VRN, VYN, VBN are the phase voltages. These are the phase voltages. Respected phase voltages. These three voltages. And apply the KVL in this mesh. Apply the KVL in this mesh. That means between the R and Y lines. Between the R and Y lines, I will apply the KVL. Now we will get the VRY equals to VRN. VRY equals to VRN minus VRY plus VRN equals to 0. That is nothing but VRY equals to VRN. The algebraic sum of all branch voltage in a closed mesh equals to 0. So similarly, between the VYB, between the inline phases VYB, I will apply the KVL. Similarly, VYB equals to VYN. Similarly, between the VBR, apply the KVL. VBR equals to VBN. VBR equals to VBN. So therefore VYB is nothing but line voltage. VBR is nothing but line voltage. VRY is nothing but line voltages. So line voltage equals to phase voltage. Clearly we will observe that this is the phase voltage, this is the line voltage. Both are same. Between B and C phase voltage. Similarly, between A and D both are same. So phase voltage equals to line voltage. Clearly we will observe here. So three phase delta connected system, we can conclude that three phase voltage equals to line voltage. Three phase delta connected system, line voltage equals to phase voltage or phase voltage equals to line voltage. Now we will see the relationship between phase and line currents in a delta connected system. As we defined as I1, I2, I3 are the respected phase currents. IR, IY, IB. IR, IY, IB are the respected line currents. Respected line currents. Now we will see the relationship between these two currents. Now apply the KCL at point B to finding the currents. What is the relationship between phase and line currents? Now I am applying the KCL at B. Sum of incoming currents equals to sum of outgoing current. At this node or junction, incoming current equals to I1 and outgoing current equals to I1 equals to IR plus I3. IR plus I3. These two currents are leaving from this node or junction. Similarly, I will apply the KCL at point C. Sum of incoming currents. I2 equals to I2 coming towards this junction. So I2 equals to IY plus I1. These two are the leaving from this junction. Similarly, I will apply the KCL at this point, capital B. So sum of incoming current I3 is the coming towards this junction. So I3 equals to sum of incoming currents equal to sum of outgoing currents. IB plus I2. So IR equals to, from this equation, IR equals to I1 minus I3. Similarly, at point C, IY equals to I2 minus I1. Similarly, at point B, IB equals to sum of incoming current. IB equals to sum of outgoing currents. I3 minus I1. So this is the line current. These two are the vector difference between these two are the phase currents. I1, I2, I3 are the phase currents. IR, IY, IB are the line currents. So IY equals to I2 minus I1. IB equals to I3 minus I2. So IR equals to I1 minus I3. Now this it can be also written as I1 plus minus of I3. I1 plus minus I3. This is nothing but vector addition. So assume a balanced R load is connected. Assume a balanced in universe. Most of the loads are R loads only, inductive loads only. So as we know that three phase voltages are displaced by 120 degrees. Already we have seen in previous lecture for star connected system. VRN, VYN, VBN. Three phase voltages are displaced by 120 degrees. Now we will assume that load is inductive load. Load is inductive load. So that in inductive load, as we know that current lags the voltage. Respected I1 equals to respected phase current, R phase current. Similarly, I2 equals to Y phase current. I2 lags the Vy. Similarly, I3 lags the Vy. Why? Because we assumed that load is inductive load. We have taken inductive load. So now I want to draw the line current IR, vector sum of I1 plus minus I3 by using parallelogram method. So here I1 is here. I1 is here. Where is I3? I3 is here only. Positive I3. If you want to project this line exactly in 180 degrees phase shift, it will become minus I3. So this is the I1. This is the minus I3. So vector sum of these two quantities, two vectors, will give the IR. Similarly, IY equals to I2 minus I1. This is the I2. This is the, if you project this exactly opposite, minus I1. So the vector sum of these two phasors, two vectors will give the IY. Similarly, IB equals to I3 minus I2. I3 is here. minus I2. If you project this opposite exactly, it will become minus I2. Minus I2. Minus I2. So vector sum of I3 minus I2 will give the IB. So in this way, we will draw the IB. What is the phase angle between? What is the phase angle between here? I1 and minus I3 from year to year 120 degrees. From year to year 120 degrees. This IR vector, this line current will make the exactly half year. So here from year to year 30 degrees. From year to year 30 degrees. Year to year 30 degrees. Year to year 30 degrees. So what is the total angle between I1 and minus I3? It will make total 60 degrees. Exactly 60 degrees. Remaining 60 degrees will be, this is the 30 degrees and this is the 30 degrees. Total 120 degrees between these two phases, any two phases. So here 30 degrees. Exactly it will make the half. 30 degrees plus 30 degrees, 60 degrees. So similarly, by using parallelogram law for vector addition. So per balanced system, all three phase currents are equal. I1, I2, I3 equals to I phase. Similarly, I will apply the parallelogram law method for vector addition. So IR equals to, this is the line current. I have taken this phase. IR line current equals to square root of a square plus b square plus 2ab into cos theta, actual formula. Here a square is nothing but I1, b square is nothing but I3, b is nothing but I3, a is nothing but I1 and 2ab, I1, I3 into cos 60. Here I will substitute the, so for balanced system I1, I2, I3 equals to I phase. So that I phase square root of I phase square plus I phase square plus 2 I phase square into 1 by 2 cos 60. 2 will get cancelled. Finally, line current equals to root 3 times of phase current. So that finally we will get the line current equals to root 3 times of phase current in delta connected system. Similarly, Y phase also same, root 3 into phase current. IB equals to root 3 into phase current. So we can conclude that for delta connected system, line current equals to root 3 times of phase current. Root 3 times of phase current. Here we can conclude that type of connection, relationship between phase and line currents, and here third column represents relationship between phase and line voltages. Type of connection means star connection system. So line current equals to phase current for star connection system. Line voltage equals to root 3 times of phase voltage. Similarly, for delta connected system, line current equals to root 3 times of phase current. Similarly, line voltage equals to phase voltage. Thank you.